You clicked on the right video. If you've ever wondered what gives things mass, why some particles are heavier than others, or how the universe holds itself together, you're in the perfect place. Everything around you, your body, the air, the stars, exists the way it does because they all have mass. Mass is the reason particles have weight, why atoms can form, and why the universe isn't just a chaotic mess of energy. Without it, nothing as we know it would exist. In our everyday lives, we experience mass as the resistance of an object to changes in its motion. It determines how much force is required to move or stop an object. A heavier object requires more force to accelerate than a lighter one. This intuitive understanding of mass, however, only scratches the surface of its true nature. At a fundamental level, mass is a measure of an object's inertia, its resistance to acceleration. But what gives particles their intrinsic mass? Why do some particles have more mass than others? These questions have challenged physicists for generations, leading to the development of groundbreaking theories. One of the most successful theories in physics, the Standard Model, describes the fundamental particles and forces that govern our universe. It has been incredibly successful in predicting the existence and behavior of numerous particles. However, the Standard Model initially failed to explain the origin of mass itself. To address this fundamental gap in our understanding, physicists proposed the existence of a new field that permeates all of space, the Higgs field. This field, they theorized, interacts with particles, and it is this interaction that gives them their mass. Just like objects moving through honey experience resistance, particles moving through the Higgs field acquire mass. The Higgs field, however, is not just a theoretical construct. Like all fundamental fields in physics, it is associated with a corresponding particle, the Higgs boson. This particle, often dubbed the God particle due to its fundamental role in the universe, became the holy grail of particle physics. Finding the Higgs boson would be the ultimate confirmation of the Higgs field and its role in giving mass to other particles. It would validate decades of theoretical work and revolutionize our understanding of the universe. The search for the Higgs boson was a monumental undertaking, requiring the construction of the largest and most powerful particle accelerator ever built, the Large Hadron Collider at Cern. Our story begins in the early 20th century, a time of great upheaval and transformation in the world of physics. Scientists were just beginning to probe the inner workings of the atom, discovering a strange and wondrous realm of subatomic particles. The quest to understand the fundamental building blocks of matter had begun. At the forefront of this revolution were brilliant minds like Albert Einstein, Niels Bohr, and Marie Curie, whose groundbreaking theories and experiments laid the foundation for modern physics. They revealed that the atom, once thought to be indivisible, was composed of even smaller particles, electrons orbiting a nucleus of protons and neutrons. To unravel the secrets of the subatomic world, physicists needed tools of unprecedented power and precision. They embarked on a quest to build particle accelerators, massive machines capable of smashing atoms together at incredible speeds. These collisions would create showers of new particles, providing glimpses into the fundamental forces of nature. One of the first major breakthroughs came in the 1930s with the discovery of the muon, a heavier cousin of the electron. This unexpected finding hinted at a hidden layer of particles, a subatomic zoo far more diverse than anyone had imagined. As accelerators grew larger and more powerful, the pace of discovery accelerated. The 1950s and 60s saw a veritable explosion of new particles, each with its own unique properties and quirks. Physicists were overwhelmed by the sheer number and diversity of these subatomic entities. It was like trying to assemble a giant jigsaw puzzle without knowing what the final picture was supposed to be. Amidst this apparent chaos, however, patterns began to emerge. Physicists realized that these particles could be grouped into families based on their properties, like notes in a musical scale. This led to the development of the Standard Model of particle physics, a theoretical framework that sought to unify our understanding of the fundamental forces and particles of the universe. The Standard Model proposed that all matter is made up of two types of fundamental particles, quarks and leptons. Quarks combine to form protons and neutrons, the building blocks of atomic nuclei. Leptons, on the other hand, include familiar particles like electrons and their heavier cousins, muons and taus. The Standard Model proposed the existence of fundamental forces mediated by force-carrying particles. These forces included the strong force, which binds quarks together, the weak force responsible for radioactive decay, and the electromagnetic force, which governs the interactions between charged particles. The Standard Model was a triumph of theoretical physics, successfully explaining a wide range of experimental observations. All the particles in the Standard Model were treated as massless, which contradicted reality. Enter Peter Higgs and a handful of other physicists who, in the 1960s, independently proposed a revolutionary solution. They postulated the existence of a new field that permeates all of space, the Higgs field. This field, they argued, interacts with particles, and it is this interaction that gives them their mass. Imagine the Higgs field as a kind of cosmic molasses. As particles move through this field, they experience resistance, much like objects moving through honey. The more a particle interacts with the Higgs field, the more resistance it experiences, and the greater its mass. This groundbreaking idea had a profound implication. Just like other fundamental fields in physics, the Higgs field should have a corresponding particle, the Higgs boson. Finding this elusive particle would be the ultimate confirmation of the Higgs mechanism and its role in giving mass to other particles. The hunt for the Higgs boson had begun. It would be a long and arduous journey, spanning decades and involving thousands of scientists from around the world. The stakes were high, as the discovery of the Higgs boson would not only validate the Standard Model but also revolutionize our understanding of the universe and our place within it. The search for the Higgs boson was a global endeavor, requiring unprecedented collaboration and innovation. At the forefront of this scientific quest was Cern, the European Organization for Nuclear Research, home to the world's largest and most powerful particle accelerator, the Large Hadron Collider, or LHC. Imagine, if you will, a sprawling complex beneath the Swiss-French border housing a 27-kilometer ring of superconducting magnets, more powerful than any ever built. This engineering marvel, the LHC, was designed to smash protons together at near-light speeds, recreating conditions that existed fractions of a second after the Big Bang. Thousands of scientists, engineers, and technicians from over 100 countries poured their expertise and passion into this ambitious project. They represented a new generation of explorers, driven by an insatiable curiosity to unravel the mysteries of the universe at its most fundamental level. The LHC is a testament to human ingenuity, pushing the boundaries of engineering and technology. Its superconducting magnets, chilled to a temperature colder than outer space, guide two beams of protons around the ring in opposite directions, accelerating them to nearly the speed of light. At 4 points along the ring, these proton beams collide head-on in a shower of energy and subatomic particles. These collisions, occurring billions of times per second, are captured by massive detectors, each weighing thousands of tons and equipped with millions of sensors. Imagine these detectors as giant high-speed cameras, capturing the fleeting existence of particles that disappear in fractions of a second. The data from these collisions is then analyzed by a global network of computers, searching for telltale signs of the elusive Higgs boson. The energy released in these proton collisions is immense, momentarily recreating the extreme conditions that existed just after the Big Bang. It is in this fiery crucible that physicists hope to create and detect the Higgs boson, a particle so fundamental that it played a crucial role in shaping the universe as we know it. The challenge, however, lay in distinguishing the Higgs boson from the myriad other particles produced in these collisions. It was like searching for a single specific grain of sand on a vast beach, requiring sophisticated algorithms and painstaking analysis. Years of meticulous data collection and analysis followed, with physicists around the world eagerly awaiting news of a breakthrough. The pressure was immense, as the discovery of the Higgs boson would not only confirm a cornerstone of the Standard Model, but also open new frontiers in our understanding of the universe. On July 4, 2012, the scientific world held its breath as researchers at Cern announced the discovery of a new particle, consistent with the long-sought Higgs boson. The excitement was palpable, as decades of theoretical work and experimental effort culminated in this historic moment. The data from the LHC experiments, ATLAS and CMS, showed an unmistakable bump in the data, a clear signal of a new particle with a mass of approximately 125 gigaelectronvolts, precisely the mass range predicted for the Higgs boson. This discovery sent shockwaves through the scientific community and beyond, capturing the imagination of the public and solidifying the Standard Model as the most successful theory of particle physics to date. The Higgs boson, once a theoretical curiosity, had become a tangible reality, but this was not the end of the story. Imagine the universe as a vast empty space, yeah? Now imagine this space is filled with a kind of invisible treacle, a cosmic molasses if you will. This, my friends, is the Higgs field. It's everywhere, all around us, even permeating through us right now. Can't see it, can't touch it, but it's there, playing a fundamental role in shaping our reality. Now this Higgs field, it's not just sitting there doing nothing, it interacts with particles, you see, and this interaction is what gives them their mass. Think of it like this. Imagine you're trying to walk through a swimming pool full of treacle. It's going to be a right struggle, isn't it? You'd feel a resistance, a kind of drag. That's what's happening to particles in the Higgs field. The more they interact with this field, the more resistance they experience, and the more massive they become. It's like trying to push a bowling ball through treacle compared to a tiny marble. The bowling ball's going to have a much tougher time, right? That's because it's interacting more strongly with the treacle, just like a massive particle interacts more strongly with the Higgs field. So, there you have it. The Higgs field, this invisible cosmic treacle, is the key to understanding why things have mass. It's the missing piece of the puzzle that physicists had been searching for decades. Now let's dive a bit deeper into how this Higgs field actually works, eh? You see, in the world of quantum mechanics, everything is made up of fields. There's an electromagnetic field, a gravitational field, and of course our friend the Higgs field. Each of these fields has a corresponding particle associated with it. For example, the electromagnetic field is associated with photons, the particles of light, and the gravitational field is thought to be associated with gravitons, although we haven't actually detected those yet. Now the Higgs field is no different. It has its own special particle, and that's the famous Higgs boson. Think of the Higgs boson as a little ripple in the Higgs field. When particles interact with this field, they're essentially bumping into these Higgs bosons, and it's these interactions that give them their mass. The more they interact, the more massive they become. It's a bit like a celebrity walking through a crowded room, right? Some celebrities, they just breeze through, not much interaction. But others, they get swarmed, bombarded by fans, they can barely move, same with particles in the Higgs field. Some sail through light as a feather, others get bogged down, heavy as a neutron star. Now, the discovery of the Higgs boson, it was a huge step forward, no doubt. But it also opened up a whole new can of worms, you see. It raised more questions than it answered. For example, why does the Higgs field have the strength it does? Why do particles interact with it differently, leading to such a wide range of masses? And what about dark matter and dark energy, these mysterious substances that make up the vast majority of the universe? Does the Higgs field play a role in their existence? We just don't know yet. And that's the beauty of science, isn't it? Every discovery leads to more questions, more mysteries to unravel. The Higgs boson, it's just the beginning. There's still so much we don't know about the universe and the fundamental laws that govern it. But we're on a journey of discovery, a quest to understand our place in the cosmos. And the Higgs boson, it's a shining beacon, guiding us towards new frontiers of knowledge. Without the Higgs field and its associated particle, our universe would be a vastly different place. Stars, planets, even you and I wouldn't exist as we know it. Think about it. Without mass, particles would simply zip through the universe at the speed of light. No clumping together to form atoms, no intricate dance of molecules, no complex structures that make life possible. The Higgs field acts like a cosmic anchor, giving substance to the building blocks of matter, shaping the universe we inhabit. The Higgs boson has opened a new chapter in physics, one filled with tantalizing possibilities and profound implications. So what are your thoughts on this incredible discovery? What questions do you have about the Higgs boson and the mysteries it continues to unravel? Share your thoughts and questions in the comments below. Let's keep the conversation going and explore the wonders of the universe together. The universe is waiting to be explored, and the Higgs boson is just the beginning. Until next time, keep questioning, keep exploring, and never stop being curious about the world around you. Thank you for joining us on this journey through the Higgs boson. Please like and share the video, and please do not forget to subscribe for more videos.